It weighs over 15 tonnes, it's about 10 metres long and 230 millimetres thick, and it's a scorching 1,200 degrees Celsius in temperature. So just how do you turn this enormous slab of iron into a sheet that's thin enough to make tin cans? At Corus's hot rolling mill in South Wales, special machinery ensures the process is efficient, precise and safe. The key to keeping the work on track are the sensors which monitor and control the manufacturing.
In the hot rolling process, we reduce slab that we've made in the steel making process. We reduce that right down to a thin coil which can only be 1.6 millimeters in gauge or a depth, but is actually about 1 kilometer long. We have immense forces at work here. We have very, very high temperatures at work here and immense quantities as well. So we've got all that huge amount of material which is being shunted around and changed in shape, and therefore we need sensors to detect every possible movement and to monitor where it's going and what shape it's coming out in at the other end of the process. And in the hot rolling mill process, it's probably one of the most important places to be using sensors, because when we waste material there, it's money down the drain.
So how exactly is the operation carried out? And how do engineers measure and control factors such as temperature, thickness, flow and position?
On the displays here, we measure using X-rays, which emit X-rays through the steel and detect on the other side. This information is then fed back to the screens you can see behind me. The width is measured using our width gauge shown on display here. It uses the light coming off the red hot steel. It detects this information and then feeds it back for us to display.
Other critical factors in the process are the thickness and width of the slab as it's rolled out. The team must get this absolutely right. Again, sensors help to monitor the process.
For example, if the gauge goes out of specification, this information is fed back instantly, which then can be rectified during the process to try and save as much as the coil as possible. Because if we didn't have this feedback, then you could lose a substantial amount of money and time. For example, each coil is worth £10,000, which would be lost, and also 1.5 minutes for each coil. Therefore, you're losing downtime because you can't roll.
This damaged coil could have been enough steel to make 5 family cars or about 200,000 beverage cans. Because the mill is continuously at work, the results from the sensors are fed into a complex mathematical norm, and the mill computer learns from the feedback. If the results produced from a sensor deviate dramatically from a norm, an error alert will be created. The overshot result may well be caused by a setup fault, or it could indicate something more sinister. Water is used both to cool the iron and to remove oxides. It's important that the flow is consistent, so once again sensors keep track.
All our instruments are protected. We're also known as IP. Our instruments here are IP68, which basically means that they can be submersible into water, dust, as there's a lot around and stuff could be sprayed onto them.
For engineers, it's not necessary to constantly look at the gauges and screens, however. Each of the sensors in the process sends the information that they record to a computer. This compares the actual measurement from the steel slab with an ideal target, allowing the team to make any necessary adjustments to the process.
This is coming through what we call the HSB mill. It passes through various sensors which are called HMDs, which are called hot metal detectors. Here comes the bar, it passes one sensor, it passes the next sensor, then it enters the roughing mill.
When it comes to achieving perfect results, computer-aided engineering ensures that errors or inconsistencies are quickly identified and put right. So when it comes to turning a 10-metre slab of steel into a 1 kilometre long coil in less than 10 minutes, it's the sensors that ultimately give the team control.